Can you find the total current flowing in this circuit? If you cannot, I'm going to be teaching you everything you need to know about parallel and series connection in this video. Now, the first thing is that we need to be able to identify when we have a parallel connection and when we have a series connection. In a circuit like this, there's a combination of both parallel and series connection. So how do you figure out which one is the correct one? All you have to do is to start from the positive terminal of the battery, and this is it right here. Now, if you go through this positive terminal and you go in this direction, then you get to a point here. Now, this point is a junction. How do you now know which one is in parallel and which one is in series? Whenever you get to a junction, what happens is that the current I that is flowing through this guy is splitted into different parts. In this case, you can name this one part 1 and you can name this one part 2. So you can call this guy I1 and you can call this guy I2. So you've been able to split the current going into this place into two parts, I1 and what? And I2. Therefore, that implies that whatever is in the path of this guy, of I1, is going to be in parallel connection with whatever is in the path of I2. So we proceed again. I1 keeps traveling and gets to another junction. So after making it through 15 ohms, it gets to another junction. Now, one thing about I1 is that at this junction again, I1 is going to split. I1 is going to split into, let's say, for instance, now we can make it I1A, and then let's say it's split into this place. We can make it I1B. So what I've done here is that the current entering this junction is I1, but at the junction, it's split into two parts, I1A and I1B. Therefore, that implies that whatever is in this B and whatever is in this A, they will be in parallel connection. And the way to now identify series connection is that when the current is flowing in the circuit, such that it is going to have to get into one resistor before it gets into the other, then such resistors are said to be in series. What do I mean? For example, if you look at I1A here, I1A will have to go through the 19 ohm resistor before it enters the 5 ohm resistor. Therefore, since I1A is the guy flowing through the 19 ohms and the 5 ohms, and it has to get to the 19 ohms before it gets to the 5 ohms, then you can say that the 19 ohm resistor and the 5 ohm resistor are both in series connection. So key point here, to identify series connection, for series connection, whenever two resistors are in series, it implies that the same current will be flowing through them. That's the number one thing. But this current will have to be done with one before it enters the other. But whenever two resistors are in parallel, or even more resistors are in parallel, it happens that there will be a junction and the current will have to split itself. So the current may not necessarily be the same that will be going into the two resistors. The current is going to have to split itself before it can enter the two of them. That is basically how you identify series and parallel connection. Now, in this situation, we are not done with the entire analysis of the circuit. What happens here is that I1A travels through the 19 ohms resistor, then it goes into the 5 ohm resistor, and just before this new junction, we still have I1A. And I1B goes through this 8 ohm resistor, and just before the junction, we still have I1B in that place. What happens to them is that these two guys will meet at this next junction. And don't forget their origin. What splitted into these two was the I1A that made it to this junction in the first place. This particular I1A. So it was this particular I1A that made it to this junction in the first place. That was what splitted to give I1A and I1B. Then when both of them regroup back at this junction, then they will become I1 again. So we have our I1 again. And let's see. So at this junction, don't forget, in the first splitting that we have for the entire current, there was I1 and there was I2. That was the splitting of the entire current itself into I1 and I2. I2 will make it through the 9 ohms resistor, and here you have I2. I1 will make it back here, so you have I1 here. And what will happen at this junction is that both I1 and I2, they will have to regroup again to form the entire current which splitted into the two of them in the first place, and that is your I. So that implies that what will be flowing through here is I. Now with this analysis now, you know those who are in parallel and those who are in series. So the origin, the whole thing started from I, splitted into I1 and I2, but I1 still had to do a lot of work, splitting into I1A and I1B. That implies that, you see, that splitting is what we have to deal with first. So we started from I, we split it into I1 and I2. So I1 got splitted again. So the more you split, you have to start from the extremely splitted current. You have to resolve those ones first. When you're done resolving those ones, then you can always come back and trace it back to your original current. So that implies that the best place to start here is with this 19 ohms and 5 ohms. From what I've explained already, I1A flows through the 19 ohm resistor. Then it will also be the one that flows through the 5 ohms resistor. Both of them are in series. So let's find the total resistance of those guys. So let me call it RT1. That is R total 1A. RT1A. What I mean by that is that the total resistance for the for the I1A, and that would be, since they are in series connection of resistance, what we do is that we add them, and that is going to be 19 plus 5. So 19 plus 5 is 24. So that's 24 ohms for the I1A. Now, we realize that I1A and I1B, both of them are in what? Both of them are in parallel connection. So I know the total in I1A. What will be the total in I1B? There is only one resistor in the path of I1B. So that implies that the total will also be what? 8 ohms. Now that I have the two of them now, I can find what the total resistance is. Normally, the general formula is that 1 over resistance 1 plus 1 over resistance 2 equals 1 over total resistance. And this can be used even when you have more than 2 resistors. But it's a very, very shortcut that you can easily use for this, such that you can know that the R total for any 2 resistors in parallel is going to be R1 multiplied by R2, everything divided by R1 plus R2. So in this situation, I can say that will be 24 multiplied by 8, everything divided by 24 plus 8. So if you do this very well on your calculator, you're going to get 24 times 8. 24 times 8 is 192. So you divide it by 24 plus 8, divided by 24 plus 8, and that is going to give us 6 ohms. 6 ohms. So we have a 6 ohm here. So what does that imply? It implies that this particular part of the O resistor, everything from these 8 ohms to these 19 ohms to these 5 ohms, all of them all together, they give a total of 6 ohms, total resistance of 6 ohms. So I've been able to analyze I1A and I1B. So don't forget, all together, when they come here, they become what? I1. Now, if you notice again, I told you that the same current will be flowing through any resistors that are in series connection. And I1 that we have just established now is the entire thing that flow through the 19 ohms, the 5 ohms, that is the 19 ohm here, the 5 ohms, and the 8 ohms. I1 is what is flowing into them, because the I1 was one that splitted into I1A and I1B. But there's another thing that I1 flows through. I1 was also the one that flowed through this guy right here, the 15 ohm here. So what does that imply? It implies that the total thing that I got for this other side, which is the 6 ohms, will be in series with the 15 ohm guy, because current 1, that is I1, is what is flowing through both of them. So therefore, I can find the total, R total, for the current 1 that is flowing now. So what would that be? That would be the sum of 15 ohms plus total of this one that I got was 6. So 15 plus 6 ohms. And if you do that together, 15 plus 6, that will be 21 ohms. 21 ohms. So with this now, I've been able to get the total resistance for I1. Now, but we don't only have I1, we also have I2. I2 only flows, so total resistance for I2 is 9 ohms, 9 ohms. And what we discovered earlier was that I1 was flowing through here and I2. So I1 and I2, they are the splitted version of the entire current flowing in the whole circuit. And that implies that I1 and I2, they are going to be in parallel. So therefore, we can find the total resistance between this RT1 and RT2. So the total resistance for the current for this one will now be, so using the same thing again, R1, R2 divided by R1 plus R2, that will be 21 multiplied by 9, everything divided by 21 plus 9. So what is 21 times 9? 21 times 9 is 189, and 21 plus 9 is 30. So we have 189 divided by 30. 189 divided by 30, that's going to give us 6.3. So 6.3 ohms. And what does this imply? It implies that this entire connection, so I'm going to delete some of the annotation that I've put here now so that you can see it more clearly. I'm going to delete some of the annotation. Okay, it seems I won't be able to do that. So look at this now. It means that this entire connection, let me just put a box around it. Yes, I think I should make the box a different color. Yeah. So this entire connection, everything here all together, I've been able to find the sum of all of them, and everything in total is 6.3 ohms. 6.3 ohms. So everything here is 6.3 ohms. And finally, what is flowing through this entire guy is the current itself, the entire current, because the entire current started from I, it splitted into I1, I2, I1 splitted into I1A and I1B, then they regrouped again and became I again. So the entire thing flowing through this guy is I. And the I is also the one flowing through the last guy here, which is the 2 ohm resistor. That implies that the 2 ohm resistor and the entire thing in this blue box, they are in series connection. And what does that imply? That implies that I will have to add them up. So adding them up implies that the total resistance, the net total resistance in the entire circuit will be the addition of the 6.3 ohms and that 2 ohms right there. So everything here is going to be 8.3 ohms. 8.3 ohms. So that is what the net resistance, the total resistance in the entire circuit is going to be. And now, don't forget the rating of this guy. The question itself wants us to find what is the value of this current. From what you know about cells, the EMF of a cell is given as I multiplied by R plus R, where this R is the total external resistance and this small r is the internal resistance. So if that is the case, the EMF has been given, the value of the EMF of the cell has been given. We have 17 volts, so that is 17. EMF equals 17. We are looking for the current. Total resistance I got here, that was 8.3, and the total internal resistance, that was that's 0.2. So what that implies is that I'm going to have 17 equals I multiplied by 8.5, and that implies that the current is going to be 17 divided by 8.5. 17 divided by 8.5 should be 2. Let me confirm that. Yeah, so that is 2 amperes. 2 amperes. So it implies that the total current in this circuit is what? Is 2 amperes. And with this result, you can actually analyze some other things. You can get the current that is flowing in each of the resistors. You can know the voltage that is flowing in each resistors. In my next video, I'm going to be explaining how you can know the voltage in each resistor and how you can know the current in each resistor. Don't forget to subscribe, like, and comment on this video if it has been helpful. I'll see you in the next one.